Great. Okay, I'll start then. So for the committee and grad students, feel free to ask questions throughout. Just unmute yourself and feel free to ask. If there's any folks here for moral support, this is definitely going to be aimed at experts, and I'm very happy to answer any and all questions, but please hold them till afterwards. And feel free to pop in and out. I'm not looking at anyone's faces right now. I'm just seeing my screen. So if you just come back at the end and say it was a great talk, I won't know the difference. If you're not following it or the sort, because you're here for moral support. And yeah, for the thesis committee, this is mostly the talk I gave for my quals last year, and there's a new result added at the end. So we'll see that. It should look pretty familiar though, but let's go ahead and start. Let me start a timer for myself. And yeah, so before, this is my dissertation talk on the utility of fine-grained complexity theory. Here at Berkeley, advised by Shafi Goldwasser and previously by Christos Papadimitriou before he moved to Columbia University. And before we can talk about the utility of fine-grained complexity theory, I first need to have a sense of what fine-grained complexity theory is. So fine-grained complexity theory, I think the best way to talk about it is to contrast it with coarse-grained complexity theory. It's never called coarse-grained complexity theory, just classical complexity theory. And it really looks at polynomial versus not polynomial distinctions. There's really a qualitative difference between what we consider easy and what we consider hard. And okay, good, I got the laser pointer working. If you're not seeing a laser pointer, please let me know. Cool. So yeah, what we consider easy and kind of what we consider hard in this qualitative sense. And fine-grained complexity theory says, okay, that's too coarse-grained. Let's look a little closer. What about n squared versus n cubed? So this is kind of usually called colloquially hardness within P. Can we talk about within polynomial time? What is the type of
Have you ever been to a thesis talk where the speaker disappeared in the middle of the talk?
Never. It's like out of that's good. I thought I disappeared, but oh, there he is. Manuel, we don't hear you. Hopefully you know that you're muted.
I see. Okay, how long was that muting?
Since the title slide.
Great. Okay, sorry about that. I will go back to the title slide.
And we can't see your screen either, it seems to me.
Okay, yeah. What happened there?
You don't have to repeat the title slide, but after that.
All right.
You were in the P versus NP being not fine-grained.
Okay, great. Let me share my screen again then. So my screen can be seen again?
Mm-hmm. Yes.
And let me close that. Great. So I'm not going to repeat the title slide, but we're talking about fine-grained complexity theory. Typically, we talk about coarse-grained complexity theory, which isn't called coarse-grained, it's just classical. And we want to look at a more kind of quantitative approach, not this qualitative easy versus hard. So you look at n squared versus n cubed. This is colloquially called hardness within P. Within polynomial time, can we talk about different levels of hardness? And kind of to get a landscape of it, it's quite simple if you oversimplify it. There's the k-sum problem, the k-clique problem, orthogonal vectors, and all pairs shortest path. Right, so these are 4 key problems that prop up 4 islands of fine-grained complexity theory. And why are these the key problems? Because they reduce to a bunch of other things that we care right? So the K-sum problem reduces to a bunch of problems in computational geometry. K-clique reduces to these language parsing, like orthogonal vectors is famous because it reduces to all these edit distance and longest common subsequence. And really what we can say is, each of these problems have, orthogonal vectors we know can be solved in quadratic time. All pair shortest path can be solved in n-cube time. And if that is as good as you can do, if you can't do any better than n squared, if you can't do any better than n cubed, well then orthogonal vectors being n squared hard makes edit distance and longest common subsequence, which is related to all these, DNA sequencing stuff. And all pair shortest path says all these graph problems are hard in the sort. So this is why we care about these problems. The hardness of these key 4 problems tells us about the hardness of a bunch of different practical problems. Great. So why is this useful? I mean, for one, it's just practical. We talk about well-studied domain-specific problems and give some hardness. We give connections of hardness between these practical, well-studied problems. And that's kind of the draw of fine-grained complexity theory. So coarse-grained complexity theory also has this draw. It's also practical. It studies well-studied domain-specific problems, but it has the advantage of not just being practical, but also philosophical. We get these meaty philosophical questions. Is it as easy to solve a problem as it is to recognize a solution? Is a world with randomness inherently richer? The BPP versus P question, the previous one was NP versus P. Can you hide secrets in hardness? This is cryptography. So, the impractical joke aside, these are all very practical, but these philosophical questions are also my favorite part of complexity theory. So kind of a question is, can we reconnect fine-grained complexity theory with these big philosophical questions? And at first glance, it's actually a little bit tricky because we don't have complexity classes for the most part in fine-grained complexity theory, because you don't have closure. If you have quadratic time reduction, if you do that a couple times, it's no longer quadratic time. You don't have nice reductions that define your complexity classes. So the question is, can we recapture these questions even though we don't have complexity classes in fine-grained complexity theory? And the point of this talk is that, yes, we can start recapturing some of these connections, and we'll look at cryptography to begin with. So yeah, let's get rid of this. And say we want to, let's define a proof of work. This is a cryptographic object introduced by Cynthia Dork and Moni Noor. And you have a verifier, you have a prover, and you have some amount of work that you want the prover to prove that they completed. So the verifier sends some challenge to the prover, and the prover should respond to the challenge by completing, this T amount of work. So for this to be a valid proof of work, and the verifier verifies it. And for this to be a valid proof of work, it has to satisfy 3 properties. The first is it should be efficient. You should actually be able to run the proof of work scheme. Namely, the verifier should be able to just generate a challenge and check a solution really fast, say quasi-linear time. And a prover should be able to solve the problem by actually putting in the work. If they want to give a solution, they should be able to put in the work, T, and produce a solution. Should be complete, as in if it produces a valid, there it goes. If you produce a valid proof, you should be able to verify that it's a valid proof. And lastly, what makes this a proof of work is hardness, that the prover actually has to put in the work to produce an accepting challenge. So namely, it requires actually T amount of time to convince the verifier. So this is the idea of a proof of work. And we could think of T of n as some n to the k, moderate hardness. We want it to actually be feasible, but actually, the prover should actually be able to do it, but give a little bit of hardness to it, n cubed or sort. And we're going to talk about this with a running example. This is one of the 4 key problems, the k-orthogonal vectors problem. Most of our results can hold for many of the other 4 things, all of them. but we're going to use k-orthogonal vectors as a running example. And the problem is you have k sets of n vectors that are d-dimensional. So, we have these n vectors here that are each d dimensions, and we're looking, think of d as some superlog. Think of it as log squared the whole time, some polylog, right? The problem is that we have these binary vectors, n binary vectors, and we want to find one vector from each of the sets such that they're orthogonal. Orthogonal in the sense that their generalized inner product is 0. Namely that when you stack them on top of each other, there's no column of all ones. So this is the orthogonal vector problem. Again, you have k sets of n vectors, each d dimension, that are binary. And you're just looking for one from each set that's orthogonal. This naively can be done in n to the k time. Again, I'm thinking of d as polylog. You just go through all possible k tuples. You just choose each possible thing and check whether it is or an orthogonal tuple or not. So naively, it can be done n to the k time. And the k-orthogonal vector conjecture is that this is the best you could do. You cannot do better than n to the k time. That is, KOV actually requires n to the k minus little o of 1 time. This little o of 1 says you can't shave anything off of that exponent. You can't shave a constant off of that exponent. So this is hard to decide in the worst case. This is the k-orthogonal vectors conjecture. And, cryptography, worst case is never good enough. You don't want it to be difficult to produce. You don't want that the proof of work, that the prover has to exert work only if they get unlucky. You want every time you submit a challenge that it will take it almost every time. So you want average case hardness. So you almost always have to have a worst case to average case reduction if you're trying to start with worst case assumptions. Also, why do we care about the KOV conjecture? It's one of the key problems. It also has this really neat connection that Seth implies, the k-orthogonal vectors conjecture, strong exponential time hypothesis. And this being that you can't do SAT better than exponential, really. But yeah, so we want a worst case to average case reduction. So one thing we do is we introduce this polynomial, which in retrospect is just a arithmetization of this. And we show that if the k-orthogonal vectors conjecture holds, worst case, then computing this polynomial, given an instance, computing this polynomial is hard on average. This is work with, here, why is it not? There we go. Marshall Ball, Alon Rosen, myself, and Prashant Nalini Vasudevan. This is average case fine-grained hardness is the paper. We show how to get average case hardness in the fine-grained world. And then once you have average case hardness in the fine-grained world, you may want to use it. And this is what we do to achieve proofs of work. So what is the challenge in proof? The challenge, you just give an instance of an input to the polynomial I just mentioned, and then you want to evaluate the polynomial, more or less. So this polynomial, because it's average case hard, the first box we get to check is hardness. Because computing this polynomial is hard almost all the time, it will actually take n to the k time to produce a solution. And the efficiency and completeness, we combine this with an MA protocol, a Merlin-Arthur protocol of Ryan Williams, to achieve efficiency and completeness as is said here. So what does this give us? This proofs of work are a neat concept, but so far they've all been heuristic, like SHA-256. Can you invert SHA-256, some hash function of the sort? They're just heuristic things that we don't have any provable guarantees on, except they're used a lot in the world, like in cryptocurrencies and the sort. So there's just these heuristic objects out there that we would like to have. And this paper here gives the first proofs of work from worst case assumptions. Right? So this is, the first proofs of work from worst case assumptions. This gives provable guarantees other than just assuming the proof of work works. So from fine-grained complexity theory, we can give the first proofs of work from worst case assumptions. also, because these problems are so structured, we get all these other nice bells and whistles. We can make the verification really fast. We can make the proof zero knowledge even. And we can, this is actually pretty crucial for what a proof of work should do. You can make them non-batchable in the sense of you can't take a bunch of different challenges and amortize the cost to do better than having to do each one individually. So yeah, this gives us some bells and whistles just by the structure of these very specific practical problems. But really the main point I want to take away here is that there's this cryptographer's dream theorem, right? You want interesting cryptography or you want efficient SAT algorithms. This basing cryptography on NP completeness. This is a dream for cryptographers. And specifically, we'd love worst case SAT algorithms, be able to get efficient worst case SAT algorithms. And because this connects by the completeness of SAT for NP to a rich theory of NP completeness. So this is what cryptographers would like. We, of course, don't achieve this, but what we do get is we get interesting cryptography or non-trivial SAT algorithms. That is, we break Seth because of its connection to orthogonal vectors. And again, this is worst case. So in this case, we can get interesting cryptography or non-trivial worst case SAT algorithms, which is informed, in this case, by a rich theory of fine-grained complexity theory instead of a rich theory of NP completeness. And really kind of the win-win here is you get proofs of work or non-trivial worst case SAT algorithms. This is kind of the takeaway of the conceptual meat, I think, of what we want to say about the proofs of work we get here. Yeah, so this is a way in which we start reconnecting back to cryptography, kind of the classical complexity theory standard. Let's talk a little bit of how we can bring randomness into the picture at all. Right, so let's do away with proofs of work. You know, the classic question of randomness in complexity theory is BPP versus P, where BPP is, you know, P, except you get to use randomness. It's efficient computation where you get to use randomness. And the famous connection is Impagliazzo and Wigderson's connection of showing that you can actually prove that BPP equals P if you have hard functions. Hardness gives you de-randomization. Unfortunately, this hardness is a little wonky. This is non-uniform hardness. Right? This is, there's some problem in E, exponential time, that requires circuits that are huge. So this is non-uniform hardness, that we want circuits. This is a great connection. Circuit complexity implies de-randomization, but we really don't understand circuit complexity that much, or we're not good at proving circuit lower bounds. And also understanding it too, just like, do we believe in non-uniform hardness? Non-uniformity can do undecidable problems. So what's one line of work in this has been trying to get, oh, sorry, before I forget. Also, I have this AE here. This is almost everywhere hardness. This is saying that there are functions for which it is almost everywhere hard, saying that for all input lengths greater than some constant, it's going to be this hard, some mildly exponential hard. And this is a fine assumption. This is what we expect, right? We expect hardness to grow asymptotically as opposed to bounce around. So we want to assume that it's hard almost everywhere, that it is just to say that the hardness grows asymptotically. So this will come back later, but it's kind of the standard assumption to get BPP equals PP. We don't want non-uniform assumptions though. And I'm assuming that people are still hearing me. I'm not just talking into the void. Okay, so
Correct.
Perfect, great. So we don't want non-uniform assumptions. So one of the great things, one line of work is to try to get it from uniform assumptions. Something like x not equal BPP gives us de-randomization. In this case, BPP in sub-exponential time, but okay. Actually, it's only for infinitely many input lengths. And okay, over any efficient input distribution on average. So this is another result some years later by Impagliazzo Wigderson. And what I want to say about this is we get this nice uniform hardness assumption. It's so much cleaner than this one. But this got really nasty. The consequent got much nastier than our nice BPP equals P. And I want to unpack this a little bit. What does all of this mean here? And the first thing I want to say is that this last line, over any efficient input distribution on an average, is not so bad, actually. That this is a fine type of tractability, a fine type of de-randomization. And why? Is it says that BPP can be de-randomized, in this case to sub-exponential time, over any efficient input distribution. That is, how do we get our inputs in the world? They come out of some natural process. We get that, like, all of the inputs that we ever come across in the world are through some efficient distribution, unless nature is doing something inefficient. So this is really saying that, you know, BPP may not be in sub-exponential time in the worst case, but anything that nature is going to throw at you, you'll do fine. Sometimes this would be called pseudo sub-exponential time. Pseudo because you couldn't tell the difference if you were an actual worst case sub-exponential time. So I want to say that this thing is fine. Just that it is, for all intents and purposes, a true de-randomization because you're not getting inputs from inefficient distributions. This one, not so much. This has been a real stickler in de-randomization from uniform assumptions since the first de-randomization from uniform assumptions, this one. And why isn't this fine? It says, yeah, you can de-randomize, but for infinitely many input lengths. What are those input lengths? I don't know. What's their relation to each other? I don't know. They could be exponentially far apart. We don't know when these input lengths occur, and we don't know any rhyme or reason to them. So this is kind of a sad state of affairs to say we have a de-randomization when we don't know when we can de-randomize or how often we can. And this has been a stickler. It's kind of part of the methodology of how to prove this result. And we'll see how to prove this result in a moment. But it really seems stuck there. And yeah, so it really seems stuck there. And in fact, what you could have infinitely often de-randomization here if you get rid of this almost everywhere. But the nice part is you don't need that infinitely often de-randomization. You can start with an almost everywhere hardness assumption and get rid of it. In uniform de-randomization, that's not the case. We cannot get rid of this just by making an AE here. So let's see what we can do about that. And kind of the first step to understanding what we can start doing here is that both of these, the first step of both of these de-randomization procedures is a worst case to average case reduction. And well, thankfully for us, we have one of those, right? We just talked about how we have this worst case to average case reduction in the fine-grained world. So we're going to use that. And what do we get? We get that if you assume the k-orthogonal vectors conjecture, then you get the same de-randomization. And in fact, we're able to get rid of the infinitely often. So this is not only a connection from the fine-grained world to classical complexity theory, de-randomization, that body of literature, but it's actually the best de-randomization you can get from uniform assumptions because we are finally able to get rid of that infinitely often qualifier. Great. So this is by Marco Carmarcino, Russell Impagliazzo, and myself. And let's talk about how we do that. So the way all of this goes, the hardness to de-randomization connection is that hardness implies de-randomization. In this case, we want uniform hardness implying de-randomization. And how are these proved? By contrapositive. If de-randomization breaks, then you don't have hardness, you have easiness. So there's a reduction that says, if de-randomization fails at some input length n, there is a reduction that actually can solve your function f, right? And where does this reduction come from? Well, you know, this paper was accepted to ICALP in Prague, and everyone there seemed to know the answer already. Like, where does this reduction R come from? Everyone in Prague seemed to know the answer. It was pseudorandom generators. Right? this long line of work where you have Nissan-Wigderson generator, pseudorandom generator, allowing you to give de-randomization. You use a hard function f to power a pseudorandom generator and de-randomize. And if that pseudorandom generator fails, as in de-randomization doesn't work, there is a reduction R that gives you this. And this is a long line of literature, a sample of a long line of literature that can do that. This last one here being how to make it uniform, this R uniform. Great. And, you know, to do this, to actually make this uniform, F needs some properties. It needs to be random self-reducible. That is, there's a worst case to average case reduction. And it needs to be downward self-reducible. And we'll talk about that definition in a second. But the main point is the polynomial FOV from our average case fine-grained hardness paper has those properties. We show that this polynomial FOV has these properties, and then we try to plug into this line of literature. Great. So let's talk about how this actually works. Yeah.
This polynomial earlier, is it of big finite field, or I mean, you mentioned that the original problem is over binary alphabet, but what about the polynomial itself?
Oh, the polynomial itself, it is over a finite field. Finite field up to n to the k, really. The first prime bigger than n to the k.
Thanks.
Right. So yeah, it's over a cross product of finite fields. So each element of your like orthogonal vector set, each element instead of binary 0, 1 is now a field element. Right. Thanks. And so, right, this long line of research shows how this can be uniform. This reduction R from broken de-randomization to a circuit F can be uniform. But there's still this oracle here to the hard function. Like, how can we use a reduction to the hard function if we think it's hard? And the way to get rid of this oracle is by exploiting downward self-reducibility. And downward self-reducibility is just that a problem can reduce to itself at a smaller input length. Right? So for example, the permanent is downward self-reducible. The Laplace expansion of minors. You have a permanent and you can reduce it to its minors of n-1 by n-1 matrices. This is a downward self-reduction. So if you could solve permanent on smaller instances, you could solve it on bigger instances. And how do we use this? Well, I don't know how to do this oracle. I don't know how to answer this oracle, but if de-randomization broke at level n-1, then I could run the same reduction, get a circuit for computing n-1, and since if you could compute size n-1, you compute it f of n, I can just go ahead and replace the oracle that was in my way by that circuit. Of course, there's still a problem here. What about that oracle? Well, you induct, right? You just induct all the way down to some constant size. If de-randomization breaks at that constant size, well, we can pull the same thing back, and since it's constant, we can just brute force this one. Just brute force those oracle calls and pass them all the way up, pass the circuits all the way up. So this is how Impagliazzo-Wigderson in 2001 achieved their result. This is why downward self-reducibility is necessary for the result. It is to remove the oracle in their reduction. Here's where the problem comes in. To have this induction work, you need de-randomization to break at every single level here. Otherwise, you won't have a circuit to pass up to the next layer. So we need an unbroken chain of broken de-randomizations. You need almost everywhere broken de-randomization. This is what I want to say. Right? That is, you need some constant such that for everything larger than that constant, you will have de-randomization break. That is, you need almost everywhere broken de-randomization. This is exactly why you need infinitely often in the original uniform assumption de-randomizations. Because what does this say? It says if you have almost every, oops, it's not what I wanted. Sorry. This says if you have almost everywhere broken de-randomization, then F is easy. the contrapositive is saying F is hard, then opposite of that, infinitely often successful de-randomization. This is why we need, this is where the infinitely often comes from. And this is what we'd want to remove, is that you need this unbroken chain of de-randomizations. Right. So how are we going to do that in the fine-grained world? We're going to exploit downward self-reducibility even more. We actually have polynomials that are embarrassingly downward self-reducible. They go down from n to square root n. So one way to say this is if you have a circuit that solves it on size root n, then you have a circuit that solves it on size n. So good. Because we have this, let's see what we can do. Now, let's say I want to solve f on inputs of length n. Well, then I know if de-randomization breaks on square root n, then I could do my usual thing. And here's my oracle. What do I do about that? Usually I'd induct, but in this case, this is fine-grained world. Everything's only moderately hard. So this can be solved in k, the kth power of this, which is just n to the k over 2 time. Right. So I can actually just brute force my oracle out of the box. And once I have this circuit, you know, I have a circuit for f of square root n, then I have a circuit for size n. So I no longer need a chain of broken de-randomization, namely no more infinitely often. So really this, it's kind of a simple idea in retrospect, but it crucially relies on the fact that we're dealing with fine-grained problems, problems that have enough structure to allow massive downward self-reducibility, and ones that are only moderately hard, because even if you could downward self-reduce permanent this much, you still couldn't answer this oracle fast enough. But because we're dealing with the fine-grained world, we can actually answer this oracle. So in this case, fine-grained complexity theory is a crucial point of trying to get rid of the infinitely often qualifier here. Good. And so yeah, again, what do we have here? We get the k-orthogonal vectors conjecture holds, we get the k-orthogonal vectors conjecture implies that we can de-randomize in a sub-exponential time over any efficient input distribution on average, as previous uniform de-randomizations could, except now without the infinitely often. Right. And we can actually do a little bit better. I'll say what that is. We can do even better. This is the k-orthogonal vectors conjecture, that slide that we've seen before. And we can actually do it from what we define as the weak k-orthogonal vectors conjecture, and it is much weaker. It says that there exists some epsilon greater than 1/2, such that it requires n to the epsilon k time to count in the worst case. That is, even if you beat n to the k time, the weak k-orthogonal vectors conjecture holds so long as you don't smash it all the way down to n to the k over 2 time. So long as you can't just beat the k-orthogonal vectors problem all the way down to the n to the k over 2 time, this still holds. And hell, you can even decide it that fast, so long as you can't count in that amount of time. So this is a very weak conjecture, and we show that, you know, the weak k-orthogonal vectors conjecture implies this as well. And just to give one last flavor of something that we show, we also show that you can solve BPP in just straight polynomial time if all you're dealing with is over the uniform distribution. So if all you care about is the fraction of inputs, not that it works on every single input distribution, which we would really prefer, but if all you care about is the fraction of inputs, then you could get it all the way down to polynomial time. This uses ideas from Goldwasser, 2002, and Kain van Malkobeek Shaltiel. Am I doing on time? Yeah, so yeah. Yeah, okay, I'll say kind of the idea of how it works. Really, it's a really clever idea of if your inputs are coming from the uniform distribution, well, how did the Nissan-Wigderson generator work? You take in a uniformly random seed and you put out pseudo-randomness. Well, if your input is from the uniform distribution, there's your uniformly random seed. So it's basically saying, when life gives you uniformly random inputs, just plug them into your Nissan-Wigderson generator. So we get the seed to the uniform, to the PRG from the input distribution itself. So that's the kind of main conceptual core of like these two papers here that we use to get this type flavor of de-randomization. And what's the takeaway from all this? Three things. One is de-randomization. We just fit into the de-randomization literature. We get the strongest results for uniform de-randomization from believable worst case assumptions. And again, this was possible because of the structure and moderate hardness of the fine-grained problems. We needed it to be massively downward self-reducible, and we needed to answer those Oracle queries by brute force. Another point is that this is a problem-centric to resource-centric connection. The problem-centric world of fine-grained complexity theory, where you're just dealing with practical problems, to the resource-centric world of caring about the resource of randomness. So again, we connect fine-grained to the structural complexity world. And lastly, this can be viewed as a barrier to proving fine-grained conjectures, lest you make a breakthrough in de-randomization, or it's a concrete pathway to de-randomization, whether you're a pessimist or optimist. Great. And also this works for K-clique too. Everything I said here, we can also do for K-clique. You could also do it from the K-sum conjecture, although you can't, with our current techniques, you can't get rid of the infinitely often, which is something we really love that we can do. So K-sum can give de-randomization, just not with the infinitely often qualifier removed. Great. So yeah, when I gave my quals talk, I kind of talked a little bit in depth on some other parts, but this is mostly where I ended. But now I want to say something about this. Since the last time I gave this talk, I want to see if we can connect to, kind of P versus NP sort of thing. So this is work in progress from that, that's being written up now from my visit to Ryan Williams this past semester. And what we're going to talk about is getting a fine-grained Carplifting theorem. First off, what's a Carplifting theorem? It's about non-uniformity. Non-uniformity is a resource. It is, we don't have non-uniformity often. So basically non-uniformity, talking about circuits instead of algorithms, instead of Turing machines. The first Carplifting theorem is this one, if you have a non-uniform easiness, if NP can be done with small circuits, then you get uniform easiness, as in the polynomial hierarchy collapses to the second level. It's a little bit weird statement, so let's look at something a little bit more familiar, or at least easier to digest. This is work that says if P space has small circuits, then P space can be done with Merlin-Arthur protocols. Of course, the thing that we would love here is if this was BPP, right? So this would make it like, if P space can be done easily with circuits, then it can be done easily with algorithms. This is what we'd want. And recently there's a paper that shows, very recently, that shows that you can almost get this if you have an MCSP oracle. Anywho, this is kind of a smattering of Carplifting theorems. The main point, though, is that, the main point is that it relates non-uniform complexity to uniform complexity. It says that, it says that if I have a non-uniform easiness, then I can have uniform easiness. And these are used to prove circuit lower bounds. They're used for de-randomization. Carplifting theorems are a big workhorse for a lot of big pieces of complexity theory. And we're going to talk a bit about this last bullet point here and what the minimum circuit size problem is, what that MCSP is. But so far, we should realize that everything so far is coarse-grained, big old P space and NP and the sort. And we're going to try to get it into the fine-grained world. And to do that, let's talk a little bit of how this last one is proved. Let's talk about how that last one is proved. To kind of get into this, we know by the famous Hill paper that if you have a one-way function, if f is a one-way function, then we can create a pseudorandom generator from it, a complex cryptographic pseudorandom generator from it. And one thing we know is what happens if the minimum circuit size problem is in BPP. So let's bring the minimum circuit size problem into the picture. I won't go into it much, except that it just takes as input a truth table and a size parameter, and it just asks, can this truth table be computed by a circuit of this size? The really only takeaway you need from this is that the minimum circuit size problem can tell hard truth tables from easy ones. If you give it a truth table, if you give it a problem, it says, this can be done by small circuits or not. This is easy or hard. And Razborov and Vertich show that cryptographic PRGs cannot exist if MCSP is in BBP. Namely, they show that natural properties show that cryptography, secret key cryptography, can exist. And minimum circuit size problem is just a souped up version of a natural property. It just tells you whether or not something is easy or hard. Again, the intuition for this is, if f is a one-way function, this thing is always computable by a small circuit, because it's meant to be efficient. A pseudorandom generator is efficient. F is efficient because it's a one-way function in one direction. So the minimum circuit size problem will always say, this is a small circuit, fine, it's an easy thing. But if you give it a random truth table, as in, yeah, if you give a random truth table, MCSP will always say hard, because most truth tables are always hard. So this is a distinguisher for the output of the pseudorandom generator, namely. Random output will say minimum circuit size problem, this is hard. A pseudorandom output is like, no, that was computable by a small circuit, because this is all efficient. And yeah, so this is the Razborov-Vertich connection. Natural properties imply you can invert one-way functions. What does this have to do with us? We haven't been talking about cryptographic PRGs. And again, most truth tables are hard by a simple counting argument. Sorry, I forgot to mention that. Yeah, we haven't been talking about cryptographic PRGs. We've been talking about complexity theoretic ones for de-randomization, the Nissan-Wigderson generator, right? This is if you have a hard function, then you can use the Nissan-Wigderson generator to de-randomize. What happens if you have MCSP here? Well, not too long ago, Marco Camersino, Russell Impagliazzo, Valentin Kabinets, and Antonina Kolokolova showed that this is actually sufficient for breaking pseudorandom generators as well. If you have MCSP and BBP, Nissan-Wigderson generator is also distinguished by it. And thus, contrapositive, F is easy. Great. So this is kind of I think, emerging classic paper that natural properties imply learning. You can learn F if you have a natural property. Great. Great. So how is this useful to us? Let's take a look at a second. Let's say F, the F I'm talking about up here, is p-space complete. Then what I'd like to say, because I know p-space complete problems happen to be random self-reducible and downward self-reducible. So because of that, I know all these arrows hold just fine. I can use a p-space complete problem F to power my Nissan-Wigderson generator. Then what I like to say, just by following this arrow, is if MCSP is in BPP, then p-space is also in BPP. This would be beautiful. I can't quite say that because if F is p-space complete, what if it has massive circuit complexity? MCSP can tell Nissan-Wigderson, oh, Nissan-Wigderson, that's a small, efficient algorithm. I can look at that. But if F is huge, then MCSP will think it's hard as well, just like a random truth table. It can't distinguish anything. So I need to have some bound on how big F is. So this is the claim that can be made and is made recently in Russell Impagliazzo, Valentin Kabinets, and Ilya Volkovich's paper that says, here's a Carplifting theorem right here. P-space in P-poly, P-space in BPP, the best one you could want, conditioned on MCSP being in BPP. So this says, if P-space is in P-poly, then F has small circuits, so then this whole thing has small circuits. Nissan-Wigderson using F has small circuits, so then this arrow holds just fine, because MCSP can distinguish. And what we want to say is, okay, what if F is instead FOV? We know this arrow holds. We've plugged FOV into the Nissan-Wigderson construction, and we can take similar steps to say this, right? That if MCSP is in BPP, then there is a fine-grained Carplifting theorem. If KOV has small circuits, as in smaller than n to the k, then KOV has small algorithms, smaller than n to the k. This is ongoing work by Marco Carmarcino, myself, and Ryan Williams. The question mark is because it's ongoing. We haven't submitted it yet. And also it's not clear if this is the full set of authors. We're talking about consequences of this possible thing with, I think, mostly these authors. Russell Impagliazzo, Valentin Cabinets, and Antonina Kolokolova before the quarantine this semester in Berkeley. Why? Right. The lower bounds reunion, the lower bound Simons reunion, they're all here. So this is ongoing work. We'll see what consequences come out of this, but let's see one corollary to this already. Right, so again, MCSP and P implies this fine-grained Carplifting theorem. The weird thing is we don't believe MCSPs in BPP, so what does any of this mean? I'm just going to show a corollary then, where all I'm going to do is I'm just going to move around these implications. They're all implications. So if I just reorder them, all I did was reorder the implications. Now I start with if KOV has small circuits, then we know MCSP, if MCSP is easy, then KOV is easy. And lastly, to finish this implication, I know Seth can't be true. This is just the connection that Seth implies KOV conjecture. Reversed, if KOV is easy, then Seth can't be true. And if that's the case, then this also holds. Namely, I just took the contrapositive of this first line. If Seth is true, then MCSP is hard. And if MCSP is hard in the worst case, then it also is hard in the average case. This is a very recent result by Shuichi Hirohara, a very exciting result. It's called non-black box worst case to average case reductions within NP. The worst case to average case reduction within NP, the problem that's in with NP that has that worst case to average case reduction is the minimum circuit size problem. If the minimum circuit size problem is hard in the worst case, it is hard on the average case. And what this says to me then is this whole thing says strong heuristica can't exist. And let me remind you what heuristica is. It's one of Russell Impagliazzo's 5 worlds. Heuristica is kind of this nice world where we might want to live in, where actually, you know, NP is hard. We don't get to solve NP. We don't get to solve NP. It's hard for randomized algorithms, but it's actually easy on average. So heuristica is the world where things are hard in the worst case, but we have heuristics for everything. So it doesn't really matter. We can solve NP for all intents and purposes because it's easy on average. Strong heuristica I'm defining here is just the strengthening of that, where it's actually really kind of saving us that things are easy on average. Where not only is NP not easy, it's super hard. Seth is true. SAT is exponentially hard, but still we have things are easy on average. So this would be a very nice, not a nice world to live in. This would be like saved at the last second type of world to live in, where things are super hard, but actually not really. And what this says is that if you could solve KOV with smaller circuits, if you could use non-uniformity as a resource to crush down the KOV conjecture just past n to the k, then you will have broken, strong heuristica. And let's take a quick look at a practical example before wrapping up. Let's say I have a proof of work based on FOV, like the one I showed earlier. Let's say I have this proof of work, and now someone gets a dedicated hardware chip, C of n, to break it. And this is pretty realistic, right? Proofs of work are used all around in cryptocurrency and the sort, and they all have these dedicated hardwares and FPGAs to like optimize breaking these proofs of work at these few input sizes. So it's very reasonable that someone may want to create a specialized computer chip to break FOV. This is where non-uniformity comes in. You have a computer chip specifically for an input size to break the proof of work, and it says, okay, if you want to break our proof of work that way, you're going to have to eliminate one of Russell's 5 worlds first. You're going to have to eliminate one of Impagliazzo's 5 worlds first, strengthened version of it. Good. So this is kind of what I want to say. Fine-grained complexity theory, we're starting to be able to reconnect back to the big philosophical structural complexity questions, right? You can't just say stuff about domain-specific problems. It doesn't exist in that vacuum. So, namely, you can't go around making claims about fine-grained complexity theory without ramifications to the classical complexity theory that we know and love. Great. And lastly, future work. So yeah, this is the last slide. Future work is just, you may want to, first off, improve our work. Can you get faster, more robust proofs of work? Can we get better de-randomizations, high end, meaning can we get it BPP to P over any efficient input distribution, not just sub-exponential time? Can we use weaker assumptions? Carplifting consequences. Oh my goodness, I think this is ongoing work, so I'm excited about this. I think there's a bunch of consequences that are always gotten out of Carplifting theorem, so I think it'd be real interesting to see what other ones, other than this strong heuristic connection, we can make out of that. Can we look at other complexity classes, space complexity? Can we reconnect to these areas? Fine-grained crypto, I think, is very fertile ground. We may want semi-anonymous cryptocurrencies. Right now, we have all this work on getting anonymous cryptocurrencies, but cryptocurrencies are also used in the black market. They're hard to audit for taxes and the sort. People are trying to make them auditable, but anonymity may kind of run counter to that. Is it possible to have something be semi-anonymous, as in only moderately hard? Can you use fine-grained to, like, it's hard to de-anonymize someone, but if you want to audit someone, you could expend the resources to do so. We know from Rodich that you can't get public key cryptography from one-way functions, at least in a black box way. But maybe you could get fine-grained public key encryption from one-way functions. It's a weaker object, and there doesn't seem barriers to do it right now. So yeah, I think fine-grained cryptography, kind of getting moderate hardness, moderately hard cryptography, cryptography that you could have even if you lived in Pesiland, possibly, is a very interesting direction with lots of things unexplored, although there are folks starting to explore that direction now since our average case fine-grained hardness paper. Yeah, I think that'll do it. Let me get my face back up here. All right, yeah, I think that finishes it. Thank you.